In this video, we're going to continue exploring RStudio, and the topic for this video is fitting classification models and assessing their performance. So the methods that we're going to look at is a single tree, and then a random forest, and then linear discriminant analysis. So those are the three classification methods that we will look at in our classification analysis. And once we've fitted each of those models, we would like to assess their performance. And to assess their performance, we're going to look at, for example, the confusion matrix. Then from the confusion matrix, you can calculate a couple of performance metrics. And to name a few, the one is the error rate, the accuracy. You can calculate sensitivity, specificity, and some more measures. And we will look at how to calculate all those measures for the models. The packages of importance over here is the carrot package. The carrot package is a powerful package which we can use to fit or to train many classification models. So it's worthwhile investigating and studying the carrot package. The R part is used to fit a single tree. The R part plot can be used to plot the single tree. And then the random forest package used to fit a random forest. Now, interesting, you can fit a random forest as well as a single tree, as well as LDA by using the carrot package. There's a nice function in the carrot package that you can use, and you can fit several classification models as well as regression models through the carrot package. So it's worthwhile investigating. Again, our tasks. First task is to install these packages. We're going to need them in the application that we're going to study. The iris dataset we're going to use. And what we're going to do with the iris data is to split it into a training data set and a test data set using the function create data partition. Okay, so this is often one of the steps that one has to do when we perform a classification analysis. So you have a training set on which you fit the model, and then to assess the model you need a test set. Okay, and so to create a training and a test set, you can use this function. Then fitting a single tree with the function rpart, and then we're going to predict. This is also a function to always keep in mind whenever you make predictions, whether we're predicting for classification models or for regression or for time series. In R, the predict function is used to predict the response of a model. And in the end, once we have the predicted values, we compare them with the actual values, and then using the function confusion matrix, we calculate the performance metrics. So we need the actual values and we need the predicted values from the model, compare the two, and then calculate a metric which will tell us whether it's a good classification model or not. The second model that we will fit is a random forest. We will use the random forest function. We will also use predict to predict the performance based on the test data. There's this nice function var_imp plot in the random forest package, and this allows us to do variable importance. Okay, so the function var_imp plot ranks the variables in the training set from important to least important. So it gives us useful information about the variables itself. And this function train is a useful function. It can fit many models, including what we've discussed, the single tree, random forest, and also other models like linear discriminant analysis, quadratic discriminant analysis, neural networks, boosting. There's many other models that you can fit using the training function in the carrot package. Okay, so carrot, the main package that we're going to explore. Okay, so again, there's a script available, and the script I call model performance script. If you look at the script, we're going to split the data. That's what the first step will be, into a test and a training data set. So we'll look at that using the create partition function. And then once we've created the split of the training data and the test data, we will fit a single tree and do some prediction with a single tree on the test data. This last line over here contains the performance metrics that we are often interested in. This is a second model, fitting a random forest on the same training data and getting the performance metric. And then over here is, you will note, I call model 3, and this is also model 3. We can call this model 3A, and this we can call model 3B. The reason why I call it a model 3 is because I'm using the train function to fit random forest and LDA. So this is just an illustration of using rpart and random forest, the functions to fit a single tree, to fit a random forest, and here I'm using the function train to fit a random forest via the carrot package. Here I use the function train to fit a linear discriminant model via the carrot package. Okay, so here the carrot package plays an important role. Okay, so in the end, I have a list containing all the performance metrics, and those metrics we can compare to see which of these models perform the best. Okay, so let's go to RStudio and let's run the script file that we just saw. Okay, so again, in RStudio, once you have that script file, once you've saved it, I'm going to open it. Dealing with model assessment. So again, notice over here, the folder that I will be working in, I call this folder model assessment because we will be fitting models, and then in the end we will assess the models. Okay, so it's fitting models as well as model assessment, and this is the script that we need to open. Okay, so here's the script again in RStudio. So let's clean our console and let's run the packages. Okay, setting my directory, always the important step. But first we need to install some packages. So hopefully you've installed these packages: carrot, random forest, rpart, and rpart plot. Okay, so let's run them, and let's run up to that line. Okay, so those packages were also needed, so R will look for them automatically. ggplot2 and the lattice package. Okay, so the next step is to again work with the iris dataset. So we've worked with iris dataset a couple of times, so let's load it again. Iris data part of the R base, so we can always have access to it. The structure, at this point it becomes important to work with the right structure. Notice if you look at the structure of the iris dataset, we have numerical variables and then we have a factor. Now it's important over here that my response, being the species, is a factor. if it wasn't a factor, then we had to convert the response to a factor, okay, by using the function as dot factor. We can convert that. Okay, so but important over here is that when we fit the models using random forest or LDA, that R recognizes the response as a factor. Otherwise, it will may think of it as a numerical variable and then fit something like a regression. Okay, so the first thing is to split the data, the iris data, into training and the test data, and this is how we can do it. Okay, so notice what's happening over here. So we use the function create data partition. Here we use the response. Okay, so in the iris data set we have species as our response, and so I just take the species and say the next argument p equal to 0.7. In other words, it will split the data into 70% for the training, and then the rest, the 30%, will be converted into the test data set. Okay, so it partitions the data 70, 30%. Okay, so that's a useful way to split it. What it does, it looks at each of the categories in the species variable and then randomly selects 70% in each of the groups of the categories, and then the 30% goes to test data. But let's look at what this command or this line will give us. So in train, that's what it looks like. Okay, so there's my resample. And notice over there it's 105. Okay, so 105 observations, and if you do the calculation, 105 divided by 150, there's a 70%. Okay, so 70% is in my in train over here. Okay, so now I can use this over here, and notice 1, 2, 3 is missing, so 3 is in the, or not in the training data set. 4, 5, 6, 7 is not over there, so 7 will be not in my training data set. So everything that's not in here will go to my test data set. So how do I create the training data? So remember, we can use the iris data set and use this vector as index. So the index just takes out the rows in the iris data set. And here I delete those rows. So if I delete the rows, it means that I'm left with the ones that belongs to the test data. So keep these, and here I say delete those. So let's create the two. So I have a test data set and I have a training data set. And if you look at the two, you can quickly, if you say test data, and you say head, there's the head for the test data, similar for the training data, and similar for the test data. You'll notice they have a similar format, okay, but different observations in the two. Okay, the first 6 and the first 6 for the two data sets. And we want to train our models on the training data. That's why we call it the training set, and then use the test data to test how good the model performs. Notice over here I have a test data set where I split the test data set further into the X, or the predictor variables. And then over here is the response. So remember, at this stage we know the actual values of the test data. So Y over here is the actual values of the test data. And we want to use only the X, or the predictor variables, to predict the response. And once we've predicted the response, we want to compare it with the actual values over here. And comparing the predicted with the actual will give us a sense of how well the model performs. So this is important, keeping only the x separate and then the y separate. Okay, so if we do that, notice it's all happening on the test. So x test, if you look at this, there's only those values from the test. Okay, so it looks like that. And if you look at y test, it's always good to make sure that you have the correct information assigned to these objects. So that's what the y test will look like. So we know these, we will predict them with the models, and then we compare them with the actual y's over here. Okay, so now we have a test set, a training set, and we can continue fitting the model. The first model that we're going to fit is a single tree, okay, using the RPart function. Notice our data is only the training data, so we ignore the original iris data, we fit the training data. Species is our response, and we say model species against all the other variables. Okay, so we specify, or we give a dot over here, and R will know it will model the response against all the predictors. So if I do this, I fit the single tree, and you can look at what the output is for the single tree. Doesn't give us anything that is useful, but notice over here we can convert this into a plot by using the rpart.plot, and that gives us a useful graph to look at. So everything that we see over here has been converted to a plot. Okay, now if you know classification trees, you will be able to interpret this graph over here. But the idea is that all the data gets poured in over here, and then along the way you ask these questions. Is the petal length less than 2.5? If yes, then you classify it as setosa. If no, then over here you split it again. Okay, so once you get to this point, you ask the question, is the petal length less than 5? Okay, and then if yes, then it goes this way. If no, then it goes that way. And eventually, all the observations goes down this diagram over here. And this question will determine whether it goes left or right. And once you are at the bottom, then that will be the group classification. Okay, so the training data will be sifted through this diagram over here. And that's what's happening over here with the prediction. So when we predict, notice over here, if we predict with the predict function, I use the object of the single tree, and then I give a test data set. Okay, notice over here that's the model that we fitted, and this is the test data that we created over there, only the predictor variables. Okay, and then I say class type equals class, because we can also get probabilities. Okay, notice over here those are probabilities over here, but we want to predict the class membership. This is the class, Setosa, versicolor, virginica. Those are the probabilities. Okay, 100% probability, 92% probability of being this, 97% probability of being this. So you can get probabilities as well for your predictions. But let's look at this part over here. Okay, so predict tree. The output over there will now be Setosa, the classes that we have in our training data set. Now this is the predictions. Now we want to compare the predictions over here with the originals. Okay, so comparing the predictions with the originals, notice there was Setosa, the model predicted it as Setosa. Okay, there was setosa, the model predicted it as setosa. Okay, but we want to do that using some metric. Okay, and the way to do that is to first calculate the confusion matrix. And notice over here the confusion matrix compares the predicted values, which we need to make a factor, and it compares it to the actual values. So predicted values and the actual values, and then this part over here, everything gives me a list of metrics that we're going to calculate. So let's run this line over here and then look at the output for this one. Okay, so what you will notice over here is the first part or first portion is the confusion matrix. Notice the predicted value, and that was the actual value over here. So 15 was correctly predicted as setosa. 14 was correctly predicted as versicolor, and 1 was wrongly predicted as virginica. Okay, so this is what we call a misclassification, and the same with the 3 over here. So 12 was correctly predicted as virginica, so it was virginica, it was predicted as virginica. This over here was virginica, but it was predicted as versicolor. So this was incorrectly predicted, this was incorrectly predicted, we call it a misclassification. And on the diagonal, you see there's the correct classifications. Okay, so correct classifications, if you add the 15 and the 14 and the 12 and you divide it by the total, you get the accuracy. So this model seems to predict the test data set quite well because it has a 91% accuracy. Okay, so 100% accuracy means all the data in the test set was predicted correctly. Some other measures, sensitivity, specificity, and so on, recall, precision. These are all measures that sometimes may be of interest. So study the definitions and when you would use these measures. Okay. For now, what we're going to look at is only the accuracy, and there's some more information around the accuracy as well that you can study. But we now have a way to obtain the goodness of fit or the performance measures for a classifier. So confusion matrix, and from this confusion matrix, all the rest of these values are calculated. There's a formula behind all of these, and there's a definition that makes a specific use of them important. Okay. Question now is, what is the structure of this outtree? Because once we know the structure, we can extract some of the values. What we may be interested in, notice over here, is the confusion matrix. So the table over here can be extracted. So going back to our object, out3, and if we say table, notice over here you can extract the confusion matrix. Okay, so confusion matrix, if you use the by class, then you can extract the other measures, these ones at the bottom. Okay, so each one of those can be extracted and you can use them for creating tables, maybe export them to a Word document and then interpret them to Word. Okay, so extracting the information that is important from this output over here, we can do that. And what I did here in C1, the object, is I've extracted the class, the by class, which contains sensitivity, specificity, and so on. I've extracted that for us. Okay, so we can run that, and then C contains these over here. The second model is a random forest. Notice over here I use the function random forest, and again a similar model is specified. Take the species in the iris data and model it as a function of all the other variables in the training data. The random forest is an extension of the single tree. It's a collection of trees, and we need to specify how many trees. Okay, so this is 500 trees, so number of trees in the forest. So the single tree, one of them, refers to what we did over here. Now there is a parameter that we need to specify for the random forest, and that parameter over here is called mtry, and at the moment I'm specifying it as 5. Okay. Again, if you study the literature on the random forest and trees, you will come across the parameters that need to be estimated. Okay, for the moment, the number of trees in the forest is 500, and the specific parameter that you can play around with is 5 over here. Changing these will change the accuracy. So if your accuracy is not satisfactory, you can always increase the number of trees and increase the parameter, then see if the prediction changes. Okay, by playing around with those numbers. But let's run the first code fitting our first random forest model. Okay, so RF, and again, you can look at the RF1. It gives us some output. Notice it gives us the confusion matrix over here, but this confusion matrix is based on the training data. Okay, so we can look at the structure of this random forest object, and we can extract any of these objects. Because this is a list with 19 objects, you can extract any of these. Predicted will give you the predicted value on the training data. There's the confusion matrix, and so on. Okay, so many of these things, if you study the random forest package, you can learn what all of these, what they mean. But you can extract them by just using the $ in the word over there. The variable importance. What's nice about the random forest, it's quite a popular model in machine learning and in statistics. The random forest can deal with categorical and numerical data, so it doesn't have a problem fitting model with mixtures of data. It's not your classical statistical approach to fitting models, but it's quite a powerful way to, and fits pretty good models to your data. The variable importance, notice there's the plot. So this plot tells us that this was the most important variable, and then the second one, and so on. So it ranks, gives us a ranking of the variable importance. So in a way, one could use this as a way to select variables. So if you wanted 2 variables, then that would be the most important variables that you would select. The petal length and width. The sepal length and width doesn't seem to be that important in the classification of the data into a species. Okay, so that's the random forest, and maybe we can run everything over here. The predict RF1, so predict random forest model 1. Again, we do something similar to what we had over there. We get the confusion matrix. Again, notice what I'm using. At this stage, we're dealing with the predicted values from the random forest. Over here, we add the predicted values from the single tree. And over here, we have the test response. And over here, we have the test response as well. So the same test response, but a different model. Okay, so different model, but we do exactly the same as what we did over there. Okay, so let's run those few lines. And again, C2 will contain some information. If you look at the confusion matrix, let's look at the output RF1. Notice over here the accuracy. Okay, so here the accuracy of the random forest is 0.95 or 95%. So the random forest over here only misclassified these two observations. Whereas a single tree, if we go back to the single tree, which was this one over here. So 4 observations was misclassified with the single tree, and only 2 misclassified with the random forest. So the random forest seemed to have improved on the accuracy of the classification. Okay, so the random forest is more accurate in terms of classifying the test data set. Okay, so that's what we would do in the end. If we fitted the different models, how do we compare them? We can use the accuracy to compare them. Or we could use sensitivity to compare different models. Up next over here is where I'm going to use the carrot package. So up to now we haven't used the carrot package, but I want to illustrate over here that you can fit the same models as you've done at the top by using the carrot package and the train function. So notice over here when I fitted the random forest, I used the function random forest from the random forest package. But here I use the train function from the carrot package. I specify exactly the same arguments. Notice over here there is some extra arguments that you can specify to incorporate the number of trees and the number of for the parameter, but you have to study the train function and look at the arguments over there. Okay, but there's a way to specify these two values in this over here. At the moment I left it out, but notice over here the training data, and here I specify only method equals RF for random forest. So the carrot package will call the random forest function from the random forest package. Okay, so even though I don't specify the random forest explicitly, it is in the back. The train function makes use of the random forest in the back. And if I run this over here, similar to what we've done so far, I can get the output using random forest. But notice, as I mentioned, the random forest being trained using the train function in carrot. So everything over here that you see is exactly sort of a repetition of what we did earlier. Always remember to use the right model. Okay, notice I use predict for my predicted, RF for the model random forest, and then there's my Y test data. Okay, so that's important to use the right objects. Out RF2, and notice over here, so this model we didn't set any parameters, but it gives us exactly the same classification accuracy as what we had over there. So since both are random forests, we would expect them to do quite similar, but over here we didn't. We kept the default. So if you want to look at the default, you can study the random forest package, see what the default is for n3 and for m3, but here they perform quite similar. The last model that I want to illustrate is the LDA. Okay, the LDA is a simple model. It is a linear model the random forest that we've looked at so far in the tree isn't linear, but the LDA finds a linear function that will separate the space of the test training data and then classify the observations according to this linear model. Okay, so again, we can use the function train in the caret package, or we can use the function LDA in the mass package. Okay, so there's different ways of training the LDA model. But what the train function does, it calls the LDA in the mass package. Okay, so the LDA doesn't need any parameters like we specified over here, so everything is estimated from the data. So running the LDA, let's look at the first line. So LDA 1, that's what it gives us, not very interesting information. Then we make a prediction, predict LDA 1. We use the LDA object and the test data, only the predictor variables. Then we have a predicted, and notice if we use predict LDA1, look at the answers, it also gave us the predicted answers. Okay, so Setosa, those were all predicted values, but we want to compare the predicted with the actual. And once we do that, we can also create the confusion matrix. So this line again gives us the confusion matrix. So let's look at out LDA1. Notice over here the LDA actually gave us accuracy of 1. So out of this analysis over here, it looks like the LDA were able to classify the test data perfectly, whereas the random forest in the single tree didn't do so well. And this may be because the iris data lends itself much more to a LDA model. The data from the random forest, from the iris data as a normal distribution, multivariate normal distributions for each of the species. And since the LDA uses the normal distribution, it does a much better job over here. Okay, so, but still there's some advantages for random forests and trees. If we had a data set that contained categorical variables, LDA wouldn't be useful in that sense. Okay, so depending on your data set, you could decide between the models, and then also given the accuracy of the models, you would choose the one with the highest accuracy. Okay, so LDA doing quite a good job for this particular example. And then finally over here, the C4 containing only the statistics that we have, or the performance metrics that's given over here, and then the list over here. Notice what I did. I created, if I transpose this matrix over here, sensitivity, specificity, all these becomes the columns, and then the classes becomes the rows. So that's the purpose of the transpose. I call it a tree. Random forest 1, random forest 2, so we fitted 2 random forests. There's the 1, there's the second one, and the last one was the LDA, which we fitted over here. Transposing the C objects, and if I run this list over here, I just get everything in a format that I can now export to Word and interpret these values. Okay, so there's my output for each of the models that I've fitted. So the output for the tree model, output for the random forest, and then the LDA at the end. Okay, and these are the output that one may be interested in interpreting. Similarly, if you wanted to get the confusion matrix, remember you could use the table instead of the by class, and then you can get these over here, the confusion matrices. You could get that in the list. Okay, so that concludes our discussion on fitting models and then getting the corresponding performance metrics to evaluate the models that we fitted. Okay, thank you.